intuition work. I feel like I guess wrong a lot.
Which is why I was saying kind of a big lesson here isn't so much like what did we end up having to do, but that if we're doing energy momentum conservation, lay out what you know about the components of the energy momentum 4-vector, both in the lab frame, also in the center of mass frame, and I'm going to, even though, I'm kind of saying the last thing I want to come back and do once you've kind of hit the point where you said, all right, now any collision decay kind of problem you give me, I can set up energy momentum equations and I can get so I have the same number of equations as unknowns. And then I would say, yeah, but sometimes there's a way to make the equations much easier to solve by thinking of Lorentz invariants. I would say, what are some things that are Lorentz scalars? And the importance of a Lorentz scalar, it will be the same value in the center of mass frame and the lab frame. But the same matter in any two, same value in any two inertial reference frames. Things that are Lorentz scalars are, of course, things like proper time, mass, and the magnitude of any 4-vector. So far I've been generating equations by saying like the components of this 4-vector before the collision and after the collision are the same. Mm-hmm. Another way I can do an end run and generate equations is saying the magnitude of this 4-vector in the lab frame should be the magnitude of the same 4-vector written in the center of mass frame. So that gives me a whole new way of generating equations, and sometimes those will be the easiest equations to solve. A second thing that we can do, and this kind of comes into play more as we do more complicated problems with more different independent 4-vectors, but if I would take the dot product of any two 4-vectors,
How much more complicated a problem are we going to look at?
I am going to have you do some problems out of Schutz that at least add enough complication that we can start seeing the power of these methods. But, if I were to say, oh yeah, I've combined this into a total momentum 4-vector, but I kind of, as I was doing this, I knew that I could write an energy momentum 4-vector for this guy and an energy momentum 4-vector for this guy. If I were going to take the dot product of those two, that should come out the same whether I do it in the lab frame or whether I do that in the center of mass frame.
Why do you... Sorry, go on.
No.
Why do you default call them 4-vectors when they're, like we just did a 3-vector?
Because the Zth component was 0, so it was... Yeah, these are 4-vectors. I just... last week when I was writing all the components, especially when we started doing matrices, you rightly pointed out, hey, you don't need to write all those goddamn zeros. But it is still a 4-vector. So on this one, there was my fourth component of my energy momentum 4-vector.
Why does it have to be a 4-vector though? Why do we need to consider that and then just say, oh, well, 0, so we're not going to look at them? But
4-vector as opposed to 3-dimensional Euclidean vector. 4-vector meaning it has a time-like component as well as space-like components.
Okay, so
the 4 is saying we have added that fourth time-like dimension in addition to our 3 space-like dimensions.
Okay.
If I'm not going to use all 3 space-like dimensions, I can leave some of them out. But yeah, we still call it a 4-vector because the 4 is really saying, don't forget you have a time component. Yeah.
Okay. Sorry, it just seems...
Yeah, no, that's...
Same 4-vector.
Yeah, no, that's a good point. That's kind of, why do you keep emphasizing 4 even if we're not going to use all 4? What I'm really emphasizing is, you call that a Lorentz vector instead of a Euclidean vector or something like that would be another way of putting it. That is why also, once we're doing problems where 4-vectors are important, I really start pushing those C=1 units because that's what allows you to have the same unit for all 4 components of your 4-vector. And again, it's not that there's 4 of them that have the same unit for your time-like component as you do for your space-like components. Does this seem like a good...
Yeah, thank you. I was just trying to skip was also thrown off by the P1, P2.
Yes, and I mean, you saw it caught me by surprise that one of them was on the y-axis. I read through that 3 times without noticing that y there, and then thought I'd read it wrong or something like that. So, yes.
The reason you said that the if we take the dot product of the 2 4 vectors in the lab frame or in the center momentum frame, we'll get the same answers because those are both 0 already, and those are...
No, it's not because of any specific reason to do with the components of these 4 vectors. If I were to tell you, okay, I've just got any 2 Lorentz 4 vectors. One of them is A naught, AX, AY, and a lot of times we say the time-like component we call the 0th component. The others we call just X, Y, and Z, or 1, 2, 3, whatever we want. And the other, so this is some 4 vector A. It might be a displacement, it might be a velocity, it might be a force, it might be a momentum. We haven't even really said what it is yet, but we know that it does follow the Lorentz geometry. If I were to do a Lorentz transform, I could run this guy through a Lorentz matrix and it would spit out the new components. And then I've got a second 4 vector B, and its components are B naught, BX, BY, BZ. Since I'm going to multiply them, they don't even have to be the same type of 4 vector. If I were going to add them, they would have to be the same. I can't add a velocity to a momentum or something like that. But I can multiply a force times a displacement or whatever I want. Now, how do I multiply 4 vectors? Well, I'm going to say, how do I multiply vectors in general? In Euclidean physics, or Euclidean geometry that we use for Newtonian physics, there's 2 main ways of multiplying vectors, dot products and cross products. The cross product, as it turns out, is actually something which is kind of unique to 3 space. You can do the equivalent of a cross product in higher numbers of dimensions, but once you start investigating tensors, a cross product is actually a way of constructing what they call an antisymmetric tensor. And never mind what that is for right now. Well, actually, no, mind what that is for right now. A tensor is a matrix. If I'm in 3 space, a matrix has 9 elements. It's going to be 3 by 3. An antisymmetric matrix would be saying if I kind of flipped it around the diagonal, it would be the same, except that everything would receive a minus sign. If this is an antisymmetric matrix, that means the diagonal must be zeros, because if I flip around the diagonal, on one hand, I haven't moved any of those elements. On the other hand, they're supposed to have picked up a minus sign. What's the only number in all of mathematics that can pick up a minus sign? You haven't changed it. It's 0. So an antisymmetric matrix always has zeros on the diagonal. And then whatever you put here, you put minus that here. Kitty cat over here, you put minus a kitty cat over here, and you put a here. No, that's too much like a 0. You put a car here, minus a car here. How many independent elements have I got there? If I wanted to tell you the components of an antisymmetric matrix, how many numbers do I have to say before you say I'll fill in the rest myself? 3, yeah. If I tell you those 3 numbers, then you can fill in those 3, and I never even need to tell you what the diagonal was. As soon as I said it was antisymmetric, you knew that was 0. So an antisymmetric matrix in 3 space happens to have 3 independent coordinates. A vector also has 3 independent coordinates. And this means it is easy, if you're in 3 space, to kind of accidentally mistake antisymmetric matrices for vectors. It turns out when you take a cross product, you're constructing an antisymmetric matrix. Why do we always treat it like it was a vector? Well, because you can kind of easily make that you can conflate them that way. But in any number of dimensions other than 3, if you're taking 2 vectors and you're using them to construct an antisymmetric matrix, you would never mistake it for another vector because the number of components would be wrong. If I add a 4th component, minus snake, minus smiley face, minus star. Oh wait, star, smiley face, snake. In 4 dimensions, my anti-symmetric matrix has 6 elements. No way I'm going to mistake it for a vector. You can do things that are like cross products of 2 4 vectors, but you end up constructing an anti-symmetric matrix, and it's got 6 independent components and so on. So so the cross product kind of was a false friend in 3 space. It turned out that some of the tricks we're using for cross products really were specific to 3 space, and we kind of want to think them through carefully again. The dot product in 3 space, though, gave you a scalar. The dot product in any number of dimensions always gives you a scalar. Dot products really are what they say on the tin. The cross product gives you an anti-symmetric matrix, and we've been thinking it gave you a vector. The dot product, we've been thinking it gave you a scalar because it really does give you a scalar. So how does the dot product work for 4 vectors? A dotted with B is A naught B naught minus A1 B1 minus A2 B2 minus A3 B3. You notice the dance of plus and minus signs is exactly what we were doing with the magnitude?
Yeah.
And that's because, hey, what is the magnitude of a vector in the first place? It's its dot product with itself, or the square root of its dot product with itself. So so you kind of say, the general thing I can tell you is take the dot product of any 2 legitimate 4 vectors, and you will get a Lorentz scalar. You'll get something that's the same no matter what reference frame you're using. And then as a special case of that, I can say, oh yeah, that means if you take the dot product of a vector with itself, you get a Lorentz scalar. And that's what we've been calling all along the interval of a displacement, or the magnitude of a 4 vector in general. So.
Okay, I think that makes sense. I'm fairly confident it makes sense.
And yes, that will be,
That makes sense.
as we go on, as we start adding kind of, more particles, more interacting things to these problems, it'll become more and more a very useful and clever trick to say sometimes instead of my equation saying, oh yeah, this component before the collision is the same as this component after the collision in the lab frame, or this component before the collision was this component after the collision in the center of mass frame, sometimes you say, hey, this particular dot product of any 2 of the vectors I'm dealing with in the center of mass frame, and that same dot product written in the lab frame have to come out the same, and sometimes that gives you a very time-saving way of writing down some easy equations to solve.
So then, this was the technique you were talking about to switch in between the lab frame and the center mass frame?
Well, this was a technique where instead of saying, I am going to set up my equations using the lab frame,
Mm-hmm.
or I'm going to set up my equations using the center mass frame,
Mm-hmm.
you set up an equation that bridges both frames. You say,
okay.
on one side of my equation, I've got the A dot B result written in the lab frame. On the other side, I've got that same A dot B result written in the center of mass frame. And maybe it's really easy to write it in the center of mass frame because maybe one of my vectors is full of zeros or some shit like this.
Yeah.
So I say, man, in the center of mass frame, I can write that result down immediately. Only maybe it doesn't it doesn't include the variables I'm trying to solve for. In the lab frame, it's kind of a longer thing to write it down, but it does include the variables I'm solving for. Mm-hmm. But sometimes you say, oh man, when the dust clears, I just wrote that one equation. I only have one unknown in it.
Okay.
Maybe over here it was easy to solve. There were no unknowns, and over here there were various things I was doing. I had to do a little more algebra, but I only have one of my unknowns. So again, a lot of times I can't count the number of times I've done problems where when they gave me the problem, I was doing matrices to switch back and forth from one frame to the other and all this. The other nice thing is, while I'm bridging the 2 frames, I did not have to do a Lorentz matrix to get back and forth between them, because kind of one side of my equation was totally written in one frame, the other side was totally written in the other frame. I never needed to do those conversions.
Seems like it shouldn't be allowed, though.
What's that?
It seems like it shouldn't be allowed.
It almost feels like you are cheating. And you say, all right, it's one thing to say, yes, I understand that a Lorentz scalar is the same in every reference frame. It's another thing to actually experience the power of the fact that Lorentz scalar is the same in every reference frame. And holy shit, yeah, I've been reciting those words. It feels like cheating when I actually use it. But so I will kind of when you're done with this problem set, I want to give you one more set of relativity problems before we move on to quantum mechanics, and these will be chosen from Schutz, and they'll just be ways of kind of showing you problems that that extend your repertoire of cool techniques a little bit.
I haven't. You go for it.
I have a logistics question.
Yes.
So if you want to ask a physics question first.
I was gonna say, if you want to like email us the problem set between now and Thursday, we could probably get started on it.
Okay. Okay, sure. So you feel like you're almost done with these? You're ready for some new ones?
Yeah.
Yeah.
Okay.
I mean, I could work on them for weeks and weeks and weeks and weeks, and just like redo the problems over and over.
But you feel like they're falling?
Yeah, the groove. Yeah.
Okay. Was that your logistics question, or?
No, mine was, when do you want us to take a midterm?
When you feel like you have mastered the relativity stuff. So I guess the remaining stuff on relativity would be some problems chosen out of Schutz. And I will ask Carlos or Marcus if they have sample midterms that I can give you from old semesters also, so that you can kind of see the format of a relativity midterm.
That'd be great.
And either it might be that they said, "Oh yeah," and then I've also got an additional one that I'm that I use that nobody's seen yet or anything like that. Or my plan was just I would make up a midterm for you, but I'll kind of, in terms of difficulty and depths of concepts and all that kind of stuff, I would use Carlos or Marcus's as a guide, since we're trying to make the classes each other.
Would you put a time limit on our tests, or?
Let's see.
And we don't want to be here like all day or anything, but
Yeah, there's something to be said for take-home tests. There's something to be said for take-home tests where you're not allowed to consult each other. You have to work independently. Let me ask Carlos and Marcus what they feel. Since we're saying we want this to be something that you can get 4D credit for,
Yeah.
let me ask what they feel is kind of the best way to make it equivalent to the 4D class.
Okay.
So there could be a time limit, or it could be could be anything from a take-home where you're allowed to work together, to a take-home where you're not allowed to work together, to a thing where you finish it within with a finite time on a given afternoon or something.
Okay. That's fair.
is there any reason that we should like go through like requesting formal accommodations for an exam that you will give us?
You tell me, okay, I've got accommodations. I say, yeah, I know you do. So it's obviously you'll get time and a half. Do you do test accommodations?
No.
Okay, so if it does have a finite amount of time, then whatever we say is the original amount of time, accommodations from the DLC gets time and a half, and it might be that turns out irrelevant if there's not a time limit in the first place. So
Okay.
I'll check with the guys. I'll ask them not only like how they usually do it, but how much do they think the testing procedures are an important part of what it means to pass 4D. It might be that they say, well, I usually give an in-class test, but if it was only 2 people, I just give them a take-home test or something. So it's I'll go by their guidelines.
Okay, cool.
Yeah, we just, if we could do anything to just like eliminate the stress of it being an exam.
Okay.
Up for that.
By the way, just in terms of the overall time the class takes, do you guys have a set time frame that you want to be done with this altogether? When are you leaving for?
Then, yeah. We're leaving August 6th.
Ooh, okay, so we do need to move with some speed, yeah.
But you wanna do it when we get back?
I was going to say, when do you start school?
Oh, not till end of September 24th.
Oh, okay. So August 6th is not necessarily a hard deadline, but it's a time that you're going to be doing some traveling. And
No, it is, because then when we get back, he has the fall semester starts like 2 days after we get back.
Okay.
Okay,
You want to work on this class, like merge your semesters? Okay, fine.
Well, maybe. Okay, let's. How about we see where we're at?
We'll see where we're at.
Okay.
It would be very convenient to be done by August 6th, but it's not. it's not like you.
I think Tori
I
might
want to
be.
be done by August
Okay,
6th.
Okay.
I don't
Okay.
want.
We will get you done by August 6th.
I don't want to like. I mean,
Okay,
this
that's
is
fair.
fun.
That's fair.
I'll continue doing modern physics after August 6th. I just.
Okay. In that case, that's a tighter deadline than I had realized we were working under. So yes, I will get you the Schutz problems as quickly as possible. We'll try to wrap up relativity, maybe take a test, probably not next Thursday or anything, but not too far after. And it might be that even as you're preparing for the relativity test, we are also moving forward with quantum mechanics material.
Okay.
Cool.
That's fine. We had a discussion towards the beginning of this that I don't know. I was feeling
Which discussion?
When I was feeling stressed about this taking a really long time, and just that I'm the kind of person that will take as long as I'm given to do something.
Mm-hmm.
And if we go faster, I'll figure it out and I'll go faster. If we go slower, I'm gonna take a long time to do things.
Okay.
I don't know.
Yeah,
if I feel that way.
I'm down. I'm down for that. We just need to, buckle down.
Okay.
Yeah.
Well, let's get you out some more relativity problems. You guys can finish writing up this the stats that we've got, and again, I won't say we need to take the relativity midterm right away because you're capable of multitasking. But I will say, okay, we should start on quantum mechanics
On Thursday.
Yeah.
Cool.
Okay, that seems like a good idea. Yeah, I also just don't want to get to a point where this is causing me any sort of stress, and I'm gonna bail on the official class thing if it starts doing that, which I don't want to do, but I just don't have energy to be stressed about a class.
Okay. Well, hopefully we'll try to run the midterm in whatever is the least stressful way that's still compatible with it being an official class.
Yeah.
Or you can say, all right, no, I'm officially going to say it's not an official class. So.
I mean, I'm enjoying this. I'm having fun. I definitely pulled this stuff out on my plane rides
Awesome.
and enjoyed it. So.
Did you get a copy of Schutz, by the way, or?
Yeah, I have one.
Yeah, I mean, if you got one between the two of you, that's good every time, except for the times that you're in different cities, and that might not happen again before the end. So.
Yeah.
It's a rare thing that we're not.
And
It's rare that we're as rare as it is that we're in different cities. It's even rare that we're in different rooms. So
Okay.
it's not a huge problem.
it's not entirely true.
I need a copy of Schutz for each end of the room.
True. Okay.
That's fair.
Yeah. I'll get a copy.
I'm not assigning you to it or anything like that. I was just curious. But
And for quantum, you said we should buy or use.
For quantum, Tipler is probably fine. I mean, I'm not crazy about Tipler, but I mean, for relativity, for example, I think Schutz is a lot better than Tipler. For quantum, I don't have any undergraduate, There are texts I like for something that would be like the equivalent of Physics 134 at UC or something. So these are junior and senior level undergraduate classes. But that's not what this one is. This one is equivalent of 101B at UCSC, at least before they changed the class numbering system there. And for that level of quantum mechanics, which is kind of a quick first look at the concepts,
So there's really a freshman level class.
this is like a sophomore level class.
Okay.
This is the if you were starting from the beginning as a physics major at UCSC, you would take the Physics 5 series, which is kind of a slightly souped up version of the Physics 4 series. Slightly souped up just because its intended audience is specifically physics majors rather than physics majors and engineers and chemists and everyone. Yeah. The at the end of that, you would take 101A and B. And they've rearranged that a little bit. Now they've merged those into one class, and I haven't really paid attention to exactly how they've done it.
Mm-hmm.
But at the end of that, so you 3/4 of your freshman year, and then 5D would be first quarter of your sophomore year, and then winter of your sophomore year, you take the modern physics class. So it's not quite an upper division class, but it's It might be a little, very slightly more ambitious than 4D is here, but it's kind of it's a weird in between class, and you will come back later and take a real quantum mechanics class. You don't come back later and take a real relativity class. So you'd say kind of its role is in the role of the relativity half of it is kind of meant to be a capstone role. This is what you're going to learn about special relativity as an undergraduate. You can take an optional general relativity class if you want, but you don't really do. But in other contexts, it's kind of capping out what you're going to learn about special relativity. The 101B is not by any stretch of the imagination capping out what you're going to learn about quantum mechanics. So for a first look quantum mechanics book, I don't have any ones that I really am crazy about. We could have you working to an extent with Griffiths, which is what you would use for that junior level quantum mechanics class. And it's kind of a little bit more advanced. I mean, especially since we kind of, if we had all summer, I could say, we'll just go a little bit more advanced. Since we won't, Griffiths will be kind of a little bit awkwardly. Well, it's just that not hard, but the pace he sets is as if he's going to, as if you're going to, have a longer time to go through this. Tipler is designed for one of those first look classes. So I would say, Tipler's not awesome, but Tipler's okay. So Tipler would probably be what to use for one of those.
And you got Tipler from the library, right?
I do, yeah. I found one, so I'll be able to check it out for most of this.
Cool.
And I found an older version PDF of Tipler that seems like it's
sufficient.
the same. But I can get it out to you.
Cool.
So cool mechanics. Definitely enjoyed the 3 days of quantum mechanics I did in 4C.
Nice.
Could I ask you a question about 8 now?
Yes. So 8, beam of high energy protons collides with protons at rest. Neutral pions are produced, and once again we're trying to find the threshold energy.
Mm-hmm.
Which once again means we take that final set of particles and we treat them as a
Moving lump.
moving lump, exactly. So we've got an M blob, which is 2 proton masses and a pion mass, and we've got an M proton, which is the mass of the single particles before the collision.
Mm-hmm.
Okay, what are your thoughts on this one? Or what are the issues that you've been struggling with on this one?
We worked on this one last class, and you started talking about the. So we decided that it was easiest to solve it in the center of momentum frame.
Yeah.
So we did that, and we solved for V. And then you kind of started talking about how we'd switch back to the lab frame.
Yes.
But that's kind of where Tori had to go, and we kind of got cut off, and I didn't really understand how to switch.
Okay. Anytime you are trying to take a 4-vector, and a 4-vector can mean a time position 4-vector,
Mm-hmm.
or an energy momentum 4-vector, or anything else. There's, force is represented as a 4-vector eventually, and so on. So anytime you're trying to take a 4-vector and you know its coordinates in one frame, or its components, I guess you'd say in one frame. Coordinates is more specific to displacement. So you know its components in one frame, and you're trying to write its components in another frame. Lorentz matrix is, always a valid way of getting from one frame to the other. So for the particles collide and become a blob, and really, nothing special about the pion. They could have collided and produced any set of particles as long as none of the output particles are what? What's the only thing that I could not group into that blob?
Just ask that question again, sorry.
Okay, so I have my particles colliding.
Mm-hmm.
They are producing a set of material particles, and I don't really care if it's pion or if it's... They couldn't be photons, exactly. A photon cannot be glommed together as part of that blob.
Oh, okay, gotcha.
Anything else could. And if I'm right at the threshold energy, anything else will, because, in the center of mass frame, I'd say if I'm creating my particles, but I'm exactly at threshold energy, then I don't give them any additional kinetic energy to separate with. So, in this one, you'd say, before the collision, we had...
Pen?
Should I reuse this space, or should I use another space?
Whatever you want to do, I don't care. I have that written down.
Okay. Yeah. Actually, let's leave that up there just in case. So as long as I'm not making anybody crane their necks too hard, over here. So in the lab frame, we had our proton. I'll call that little m, and it had momentum p naught. It was going to hit a proton which was at rest. So if I was going to write the energy momentum 4 vector before the collision, and while I'm saying 4 vector just because I'm emphasizing it's got a time-like component, now there's only 2 components I actually care about. So I would say this will be m, I could say m plus m gamma, or I could say m plus the root of m squared plus p naught squared. And this is just saying, do I want to think of v as my main important variable, or do I want to think of momentum as my main important variable? And usually in these collision problems, momentum is a more convenient one. And then what was my momentum? It was p naught. After the collision, I've got my blob. I'm just going to use big M as m blob, which is 2m proton plus m pion in this case. So the big M will just be my blob mass, and it is still moving with momentum p final, except that in this case, clearly, as I said, momentum conservation tells me, okay, P initial must be the same thing as P final. So bringing all those together, that's saying, okay, this P final is really the same thing as P initial, M plus the square root of M squared plus P naught squared equals the square root of big M squared plus P naught squared. And that looks like one equation and one unknown, so I could probably work to isolate P naught and solve for it. So there's kind of my setup in my lab frame. What's my setup in my center of mass frame?
The 2 protons are going at each
I'll
other.
call this PCM or P2 or whatever. It's a different amount of momentum than we had over here. What's it look like after the collision? Blob, and it's at rest. So what do my energies look like? Here I have 2 times the square root of m squared plus p2 squared. And 0, because those momenta add up to 0. Over here, I've got big M. 0. And looking at this, here I've got the problem that I have to square both sides to get rid of those square roots, but no matter where I put that extra little m, I'm going to get cross terms when I square both sides, so then I'm going to still have at least one square root.
Yeah.
And I can move everything over to the other side and square both sides again, but I'm kind of getting telescoping algebra as I do that. Whereas over here, it's pretty damn easy to set this equal and solve for P2. So and, in fact, if I do that, okay, so I divide out that 2, square both sides, it looks like I'm getting P2 equals the square root of m squared over 4 minus little m squared.
Mm-hmm.
All right, and since I know big M and the blob, and I know little m the proton, I can get an actual value for P2. Now, only problem is this is the momentum in the center of mass frame. It was easy to get, but it's not the frame that I want. Mm-hmm. How do I get back to the lab frame?
Lorentz transform.
Lorentz transform. Now I gotta say, okay, how fast is the Lorentz transform? Well, if I knew the velocity of these particles in the center of mass frame, that actually is the velocity of my Lorentz transform, because I want to transform back into a frame where this guy is at rest. So my lab frame, this is a billboard marked lab frame, my billboard is actually coasting along with that particle. So if I know that particle's velocity, I also know the velocity of the Lorentz transform that I need to do. What's this particle's velocity? Easiest trick is the famous momentum over energy. I know this particle's momentum, I just solved for it. I know its energy, it's just that without the 2 on it. So I've got numbers for both of those. Take momentum over energy, that should tell me the speed of the particle. And because we are in c=1 units, velocities are dimensionless quantities. So that number should come out between what and what?
0.
Between 0 and 1. If it doesn't, something's gone terribly wrong.
Yeah.
So I go ahead and do that, and then I'd say, okay, so my lab frame's moving along to the left like that. What is my... Now we were trying to find the threshold momentum or the threshold energy of this guy. So I want... the energy momentum vector of the left-hand proton, the incoming proton, in the left lab frame. Well, in the center of mass frame, this proton specifically has energy, looks like that, and momentum that looks like that. So I can write his energy momentum vector in the center of mass frame. What does it look like in the lab frame? Energy E threshold, momentum P naught. So, momentum in the lab frame equals a Lorentz matrix times that same energy momentum vector in the center of mass frame. Okay, so those are numbers. The velocity of the lab frame relative to the center of mass frame. Which way is the lab frame going relative to the center of mass frame? Left or right?
Left.
Left. So this velocity is going to be negative, and it's going to be P2 over E2. So these are all things I've found. I mean, it kind of looks like an annoying little bit of algebra, but these are all things I've already found and I've put numbers to.
Yeah.
All right, so I get that velocity. How do I build my Lorentz matrix? Well, if you know a velocity, how do you build a Lorentz matrix?
The 4 vector and the velocity, the gammas and the negative.
Normally I write minus V gamma, except that in this case V is negative. So these do become positive terms.
We still write negative v gamma.
I could do that if I want, but I can then say, but I remind myself that V itself is negative. So these two matrix elements are positive numbers.
It'll become positive, yeah.
They will become positive numbers, yeah.
Oh, it seems like such a bad idea to get rid of the negative.
Okay, no, I'll write it like that, but I will also put a little note to myself that says this whole blob here is a positive number. Yeah. It depends. I mean, if I get rid of the minus, I could be saying the convention is v means now speed rather than velocity, or something like that. But though the same way it would be in Newtonian physics, either convention is fine as long as you make it and you stick with it. I mean, if I was doing a regular old Newtonian inelastic collision and one object was moving to the left, yeah, I could say its momentum is negative mv, Or I could say its momentum is mv and v is negative blah blah blah. So
yeah, it just depends on what you're more likely to forget.
yeah.
I guess.
All right, but this is something that, you've got all the ingredients you need to set it up. You have found your P2, which means that you've got actual numbers for that momentum and that energy, which means you've got an actual number for that velocity. And as you're building this matrix, which means now you've got an actual number for gamma, and you build this matrix just based on the actual numbers. I would say you don't try to do algebra where the gamma is square root of 1 over 1 minus v squared and all that kind of thing. You just say, now let me calculate actual numbers here and here, plow them through, and what I don't even need to do the lower component, whatever I get for that top component, that's my E threshold.
It was a very concise way of doing this problem. That wasn't quite doing. Maybe I was just doing a lot of filler calculations that were kind of unnecessary.
Well, I mean, it's easy to chase yourself around in circles because there are many ways I can set up valid equations.
Yeah.
We were saying here, I can set up valid equations in the lab frame. I can set up valid equations in the center mass frame. I can set up valid equations using invariants that span the frames. And yes, it's real easy to fall into just kind of ending up using too many of these things. Not limiting myself to just because I could write an equation doesn't mean I need to write that equation. And again, the last thing, and as we approach, so next week we will be kind of wearing two hats. We will be starting quantum mechanics, and we will be getting you ready for the relativity test. And part of getting you ready for the relativity test is going to be, once you've kind of written up and are happy with all of these problems, I do want to kind of show you both some slightly more advanced problems and methods which are not as obvious as the ones we've been doing, but can save a lot of time. And the methods I'm talking about are mostly these Lorentz invariant things that we've been saying here. But for the most part, for the exam, if you think of a clever Lorentz invariant way to do an exam problem, that's awesome. I won't write exam problems where you are expected to think of a clever Lorentz invariant way of doing it.
That's good to know. Appreciate that.
So you had been asking about number 7 and number 8. What was the interesting thing on number 10?
I just hadn't gotten a chance to.
Oh, just haven't gotten the chance to do it yet.
Yeah.
Okay. So I will. And again, number 10 is probably you will find it more straightforward and than the Let's see if there's any twists. The pion has a lifetime of blah blah blah. Give you its gamma factor, and they ask how far it travels before it decays. Because its gamma factor is several hundred, one thing this means is, in the lab frame, how far does it travel? Well, v times the amount of time it takes, but it's going to be moving so close to c that you are allowed something like this to say, once I figure out how much, I know how much time it lasts in its own rest frame. I can figure out how much time it lasts for in the lab frame. I also can, if I want, figure out its speed in the rest frame. I mean, hell, I know its momentum. I know its energy. Speed is energy over momentum and all that kind of thing. So I could take that gamma and just solve for v. It's going to be kind of a pain because the gamma is so big that on my calculator, things will cancel out to many decimal places. I'll need to remember to keep the extra decimal places.
Yeah.
But I can solve for v just take it. I can solve for v just using the gamma formula. I could solve for v more easily using momentum over energy, or at least I don't need to keep as many decimals on my calculator to get that to work. Mm-hmm. Or I could not bother to solve for v, and I could say, once I know how much time it lasts in the lab frame, the thing's moving at the speed of light. I mean, it's, a fraction of a percent short of the speed of light. So I could also just take c times that amount of time and say that's a pretty good estimate right there.
Yeah.
But yeah, and then in part C, they finally do ask you some energy momentum conservation things where you need to do it quantitatively, but again, it should be a pretty easy one compared to the ones that you've been doing up until then. All right. So while you kind of finish your thoughts and write-ups and collecting things on those two, and while you tackle problem number 10, would you like to go and start taking a look at some quantum mechanics today?
Sure. Could I ask you one quick question first? So, I think this should be quick, but, so, kind of just going back, to, like, last week, so, like, space is infinitely length contracted for light.
If you try to switch it to the rest frame of a photon, then yes, you will squish your space-time into a pancake.
But from our frame of reference, shouldn't light also be, like,
Yes.
infinitely length contracted?
Yes, if you wanted, you could say that the... okay, so there's an interesting thing. You could say... When I say that space-time squishes into a pancake if you try to chase down a photon, it's because I'm saying, hey, some finite length that we would measure, from the photon's point of view, that gets squished down to nothing. So we'd say, does the photon feel like it lives in a two-dimensional universe? Well, you could actually, if you want, say no, because you could say, if I'm treating the photon itself as a point in our rest frame, in our lab frame, a moving point, but a point, at any given point along the trajectory, it takes up zero volume. You could say, well, what does the photon look like in its own frame? We are seeing it having already been length contracted by a factor of infinity. So if you wanted, you could say, hey, in its own rest frame, maybe that photon is actually this long strung out string, and then we'd kind of say, but there's no points. The points in front of it and behind it have squished into a pancake, but you could say that's okay. The photon itself now takes up a longer space and fills that missing axis. So I suppose you could say that restores the photon's experience of space-time back into a four-dimensional thing, because you've squished one dimension, but you've also infinitely expanded the space the photon itself takes up to replace that dimension.
I think that just made my brain hurt more.
Yes, it is not something that you need. To the best of my knowledge, there are no practical problems in relativity that hinge on that question. But you could, if you're saying, yeah, but I just want to put myself in the shoes of a photon and wonder what the universe would look like to it. Yeah, maybe you wouldn't have to say it looks like a pancake. You'd say, well, it's the spaces in front of it and behind it have been squished into a pancake, but that dimensionless point of space that it takes up has been pulled out into a string to make up for that.
Oh, man.
What you do want to remember is this is the limiting case of the question of what do really fast-moving particles look like. And you'd say, yeah, in that limiting case, if I've got a very fast-moving spaceship, it gets, I measure it to be to be taking up almost a flat region of space here. The people on board the spaceship don't measure it that way. They measure it to be its normal rest length. And in fact, they would say my lab is the thing that's taking up a flat pancake region of space.
Okay, that was my only question.
I haven't yet told you about the Blintz transform, or what are other tasty baked goods?
The waffle matrix.
Awful theory of life. Relativity. How are those really good?
They're really sweet, but they're good. Carl?
They have like...
Paul?
I'm good, but thank you. Actually, I will try them. I'm curious about them too.
A lot of them are broken. You brought a bunch of broken ones. You should return it.
Yeah, let's go back tomorrow. They had like a bunch of interesting things.
Yeah, very sweet. You don't have to eat it, Paul.
I'll finish it, but I will take much smaller fractions of it in the future.
That's fair.
Yeah,
A lot of sugar.
It smells sweet. Wow.
That'll give you cavities.
While I was there, I got an acai bowl and they had coconut like flakes on top, but because it was so hot, they like melted together inside this like bowl of frozen things. They like melted together.
That's cool.
And at the end, I had like clumps of like coconut meat. It was really good. It was also sweet. Usually I just don't really like chunks.
All right, now I do not have a pre-made idea of like where we will start and where we will go on quantum mechanics. So let me ask you both: what smattering of quantum mechanics have you picked up in the past, and kind of we'll figure out a starting point and a good way to spend 4 weeks on this.
I just remember the ramp and like the ditch that it goes into, and then it has like a
Potential well.
threshold to get it out of the ditch.
Okay, what's the it?
I don't know. Don't remember.
Okay,
Like
So-
an electron volt or something.
So Marcus derived the Schrodinger equation in class.
okay,
And then we went into potential wells.
That's what I know. Potential wells. That's what I'm talking about. That's what the ditch is.
okay.
And I think that's it, but let me look in my notebook really quick.
Did he talk about things like the discovery of photons, the photoelectric effect?
Yeah, he talked about the photoelectric effect. He talked about stopping potential, tunneling, that's potential. This is the review. Okay, here we go. Barrier tunneling, Heisenberg uncertainty principle, infinite potential wells, Schrodinger. I talked about the Bohr model, the de Broglie hypothesis. Wait, did I say that right?
De Broglie.
De Broglie.
Very close, yeah. Let's put it this way: I've heard it massacred much worse than that. De Broglie?
De Broglie. I do that all the time.
Hospital.
Hospital. Oh no, that's worse.
Apparently, some people called special relativity special rel in Marcus's last 4D class.
Is that a problem?
To Marcus, it was apparently.
What he said in class was, if you call it special rel, I'm gonna start considering you an asshole. He said that.
Okay, fair enough. I mean, I don't know why that particular thing would be his sore point, but there are
so many worse things you could do.
I think he just.
There are things that I like, the terminology that I hate, though, so I'll respect that he's got arbitrary terminology that he hates. Amperage.
Amperage?
Is that what you mean?
I'm getting a little bit better at, hearing the word amperage without cringing.
What's amperage?
Alternate word for current. Electrical current.
Oh, because you use amps to measure current.
You use amps to measure current, so
that's
I guess
dumb.
you'd say it's like mileage for distance or voltage. See, the thing is,
Ew.
voltage I have no trouble with, though. I like the word voltage.
Yeah,
Electric potential is a terrible term.
Let's just notation-wise, electric potential is so confusing with potential energy.
Exactly. And it's, you could say, well, it has nothing to do with potential energy. Well, no, it does have something to do with potential energy. But if you start thinking they're the same thing, then you're going to start making mistakes.
You want another similar, but not the same.
Yeah. So, to me, voltage is absolutely, you don't have to call it voltage, but anything other than calling it electric potential. And yeah, I remember I was.
I agree. I don't like that.
Yeah, I was talking to a big class, and I was kind of going on my rant about how stupid the term electric potential is, and that I was saying, you'll get these snobs who don't like the word voltage, and and say that it's somehow kind of don't think I'd say this in front of a big class, but almost like a trailer trash, term or something like that. And they are nothing but snobs. The word voltage is absolutely. And after doing this big rant, then I had 3 students in a row come up to me and start talking about amperage. And I said, shit, this is my karmic penalty for that rant I just did about voltage. But yes, if special rel is to Marcus what amperage is to me, or at least was until I started getting used to it, then I can respect that.
I think that is, like, his students even made him, like, a t-shirt where his, like, head is length contracted, and it says special rel on it. It's pretty ridiculous.
It's because your length contracted, there wasn't room for all the letters anymore.
He also talked a little about general relativity, and then the ultraviolet catastrophe.
Mm-hmm.
And it's quite entertaining.
I'm really glad I got to take course with Carlos. I enjoyed that a lot last summer.
Okay.
I'm definitely glad I got to take class with Marcus.
And for Carlos's version of 4C, the things we've just been talking about, the photoelectric effect, are these all kind of the similar things to what he was covering?
It was definitely covered. The degree to which I remember it and can work with it is definitely up for question. But he talked about photoelectric effect. He talked about electric potential, or potential wells, I guess. Mm-hmm. You talked about electric potential.
The photoelectric effect, was that? No, I'm thinking of Compton scattering. We talked about Compton scattering too.
Okay, and Compton scattering. Well, Compton scattering is a relativistic energy momentum problem done before you had any way of doing relativistic energy momentum problems. So the place where the Compton scattering equation comes from, you now know. You're just saying, okay, well, I've got in my lab frame, I've got an electron at rest or a charged particle at rest. Doesn't have to be an electron. I've got a photon coming in. They hit, and rather than just a one-dimensional collision, we'd probably do the full-blown two-dimensional collision. Why do I say 2 instead of 3? Just because, well, you can just define your XY plane to be the plane of the collision, whatever it was. So the Compton scattering problem is a collision much like we're doing here. They almost certainly would not have derived where it comes from in 4C, because what they were missing was the formulas for relativistic energy and momentum for that electron after the collision.
Yeah.
Mm-hmm. Although actually, there's a classical version of the Compton scattering equation that where you don't need the relativistic thing either. So we do that. Out of all these, the thing to me that kind of broke open the fact that there had to be a field of quantum mechanics in the first place was the discovery of the photoelectric effect. So if there was one place that we were going to start, it probably would be with photoelectric effect. What is your memories of physically either what's going on in the photoelectric effect and or, equally important, what was the relevance of that experiment? What did they learn from the photoelectric effect experiments?
You're going to need to give me a sec.
I mean, it had to do with the black body radiation stuff, right?
Not directly.
It was around the same.
It was around the same time, and when I say what was the significance of it, the significance is very closely related. So the photoelectric effect experiment itself had nothing to do with black body radiation. But what came from it, yes. Both of those were experiments that could only be understood, or I shouldn't call black body radiation an experiment. It was kind of a phenomena that they had done a bunch of experiments about and still didn't understand how the hell it was supposed to be working. But both of those can only be understood once you know that...
Well, I guess I'm kind of trying to say the same thing as you, but I thought it was that, elements only emitted certain wavelengths of light because they were dropping in energy. The electrons were dropping in orbits. So it's discrete rather.
Essentially, what I was saying was going to say would be either photons exist or light is quantized, which is kind of another way of saying the same thing.
Oh, that's the photoelectric effect?
Well, that is the implication of the photoelectric effect.
Okay.
The experiment on the photoelectric effect was you shine light on a piece of metal, And you find as you vary the intensity of light and as you vary the frequency of light, the metal sometimes will be, you'll sometimes see electrons breaking loose from the metal, and other times you won't. And as you change those variables, the question of how many electrons break loose, how fast are they going, this was kind of the experimental aspect of the photoelectric effect.
They kind of found like the probability that like something would occur, right? It was the probability that the I don't know, like, right? Well, didn't it have to do with probability and not like an actual like values?
That would be kind of a later concept in quantum mechanics, the whole idea of probability waves. On the photoelectric effect, I mean, you could still say, if I send one photon worth of light down to hit that metal, sometimes an electron will break loose, sometimes it won't. But, you know, the thing that is tough to wrap your mind around about probability in quantum mechanics is that in classical mechanics, we got such a thing as probability. I flip a coin, I say it's 50-50, it'll come up heads or tails. Or I roll a fair die, and I say there's one chance in 6 that what I'm going to get is a 4 on it or something like that. But when I say that, I'm not saying that these probabilities are fundamentally built into the way nature works. I'd say no, Newtonian mechanics is 100% deterministic. As I flip that coin, as it leaves my hand, if I know the momentum and the angular momentum of that coin out to as many decimal places as I need, if I know everything that could possibly be relevant about the density of the air in the room, any currents of air that either are blowing right now or will happen to come along as the coin's going through the air, if I know everything about the initial conditions of the coin and everything it's going to interact with, there's not a 50-50 chance I'll get heads. There's actually either a 0% chance or a 100% chance. But it's just because I don't have all those variables, I don't have access to all that information, I don't know whether it's going to be heads or tails. And I kind of could say I could do some mathematics here. I could average over all the range of possible momenta that coin could have, and all the range of possible angular momenta, and all the range of atmospheric conditions that are possible in this room that I don't yet know about. And I could find, yeah, that'll give me a probability distribution of how the coin will land. And very often that probability distribution will end up saying, well, no, I was uncertain enough about a lot of those quantities that I'm still going to say it's essentially a 50-50 mix. But nature thinks it's 100% one way or the other. So that's how probability works in classical mechanics. In quantum mechanics, when we say the probability that this electron will be spinning counterclockwise is, and depending on the problem I'm doing, I might finish that sentence by saying the probability that it spin up is going to be 70%, it's going to be 2%, it's going to be 50-50, or, there different experiments can give me different results. But the thing is, this time, I'm using probability in a very, very different and much deeper way. I'm saying this time, no, even if I knew everything there is to know about the initial conditions that I'm setting up here, nature has not yet decided which way that electron is going to spin. You can still have a classical ignorance-based probability. I can still say, well, no, I actually don't know if I've set it. I don't know exactly how I've set the conditions of the experiment. I got to average over all the possible initial conditions. And then I'm getting probabilities that are kind of the way I'm used to thinking about probability in Newtonian mechanics. But I can also say, no, I have been very careful here. I know the exact initial condition of this experiment, but the laws of quantum mechanics are still telling me there's a 60-40 chance that the electron will be either spin up or spin down. And in this case, I'm kind of saying nature has not rolled the dice yet. There can be cases where I'm not saying that probability exists because of my own ignorance. I'm saying that probability exists because, given the initial conditions of the experiment, when I calculate out through Schrodinger's equations what could happen at the end, Schrodinger's equation itself gives me a probability wave. It doesn't give me an actual answer, an actual trajectory for the electron. It gives me a set of probabilities of what might happen. This annoyed the shit out of Einstein. He absolutely thought this was nonsense. It's not that he thought quantum mechanics was wrong. He didn't want to. He wasn't saying, now we should just go back to Newtonian mechanics. We had it right before. But he was saying, no, this is just a stepping stone. In the same way that the Bohr model was kind of a stopgap model until they learned some deeper stuff. He was saying quantum mechanics itself, the Schrodinger equation and everything that goes with it, this is a stopgap model. We're on our way to learn something deeper. And once we do actually figure out what deeper level was this an approximation to, it's going to be deterministic again. The reality isn't really based on probabilities, and nature herself really does know how that electron's going to end up spinning. It's just that I don't know for two reasons. I don't know because maybe I don't know because I don't know the initial conditions well enough, and that's just kind of familiar old classical probability. Also, I don't know because I'm sitting here thinking that Schrodinger's equation is a valid model for quantum mechanics, and clearly it isn't, because it gives me these nonsensical results. Clearly we're going to come up with something better. He was right that Schrodinger's equation turned out to just be a low-energy approximation to deeper models. He was wrong about those deeper models turning out to be deterministic. In fact, the more we delve deeply into quantum field theory and things like that, the more clear it's becoming that no, there really is no way you could build a deterministic model that fits even our partial understanding right now of quantum mechanics. So that's the probability stuff, and that is not what we tackle right away on the photoelectric effect. I would say the main lesson of the photoelectric effect was that photons exist in the first place, that light is not a classical wave of electric and magnetic fields, but that it also, it is a wave of electric and magnetic fields, but that also somehow it manifests as individual particles. And these 2 points of view are kind of hard to reconcile with one another. When you send a wave through a medium, you can't count how many waves are there. You can count how many cycles went by. And sometimes people make this mistake. When we say that light is quantized, they say, oh yeah, when you say one photon, that means one cycle of that light wave. And 2 photons means 2 cycles of that light. No, that's not what we're talking about. Instead, I'm saying how many, if I take a shive machine and I send a wave down it, and I say, how many waves are there? Well, you can say, are you saying how many cycles fit on the shive machine? No, I'm talking, more something like amplitude almost. Like if I were to make this wave stronger, if I would put more energy into it, I'd be giving you a larger answer here. But I want you to count how many copies of that wave exist on this shive machine. And after we've gone through all the ways you could misinterpret the question and think, how many cycles, or how many wavelengths, and I'm just saying, no, how many actual copies of that wave have I put on the shive machine? I end up saying that's nonsense. Waves are continuous. You don't count 1, 2, 3 units of waviness on the shive machine. You can count the amplitude. You can say I've got the wave with a 3 centimeter amplitude. Now it's got 3.1, 3.2. Or you can count how much energy I put into it. You can say I put in 5 millijoules of energy, and now 5.1, and now 5.2. But no, these are not discrete quantities. There's always some amount of energy in between any two that I mentioned. As it turns out with light waves, that is not the case. They are discrete quantities. And we're not talking about each cycle of the light wave as a different photon or something. We mean the waviness, how much energy I put into that thing is quantized. And the way that
energy is quantized?
The energy is quantized, or you could say the amplitude of the light wave is quantized. The amplitude of any wave is kind of closely tied to how much energy you put into the wave.
Yeah.
So you could say the amplitude of light wave is quantized. Thing is, since energy goes with amplitude squared, the amplitude is not going to be 1 unit, 2 unit, 3 unit, 4 unit. It'll be root 1, root 2, root 3, root 4. But this is something that doesn't happen classically. There is no known classical wave where you've got discrete limits on how much energy you're allowed to put into it. You could always say, well, no, let me just take the average of those last 2 values. With light waves, apparently you can't. And the evidence that led to this conclusion was evidence from the photoelectric effect, which said this. If I have got a surface of metal, and my metal naturally has conduction electrons in it. People knew that metal conducts electricity. By this time they had figured out that electrical charge is carried by protons and electrons, but since the protons tended to stay put in the nucleus of an atom, and the electrons are the ones that you can easily strip off the atom and move around, you'd say, okay, the most convenient way of carrying electrical current is to move electrons around. So I've got this piece of metal. It's got conduction electrons in it, which are free to move around wherever they want within the metal. But what they're not allowed to do is leave the metal. When I'm running electrical current through a wire, I never find that the current itself leaks out into the space around the wire or something like that. It's not that physically the electrons could never leave the wire, but it seems like, nah, they're kind of stuck in it. It would apparently take a decent amount of energy to tear them out of the wire, so it doesn't usually happen. So they started saying, okay, it doesn't usually happen. Can I explore the cases where it does happen? So I send light waves down to deliver energy to this metal. And I figure if I deliver enough energy, I can probably pop some of those electrons loose from the metal. Now, each electron has a certain amount of binding energy to the metal. Have you guys taken some chemistry?
A little bit.
The concept of binding energy is not a new one, though.
No.
If I got a chemical bond, if I want to break that bond, I've got to put in some energy, which means, and hell, this comes back to the binding energy we talked about in relativity, where we say, this means that a bound system actually has negative potential energy, and in relativity, that contributes to the mass energy of that object. But you'd say even before I was interested in looking at these subtle changes in the mass energy, and for everyday amounts of energy getting like a chemical bond, it is a subtle change to the mass energy. For a nuclear bond or something like that, it can be a more noticeable change. But even before I was interested in that, I'd say, okay, well, binding energy just means how much energy would I have to put in if I wanted to be able to break that bond apart. Again, it's kind of like, it is a threshold energy in a way, because it's saying, yeah, if I put in exactly that amount of energy, I can break the bond apart, but my two pieces have no kinetic energy left over, much like our blobs in those threshold problems we were doing. If I put in a little bit more than that binding energy, then I can break them apart and have some kinetic energy left over, and they can go flying out. So here we're saying, all right, same kind of concept. I'm trying to introduce some energy and break those electrons loose. So each electron presumably has some amount of binding energy that I've got to provide before it can break loose from there. The binding energy, they give a terrible name. What am I talking about here? Terrible name for binding energy.
You're asking us what that name is?
You just want us to agree.
No. What is the terrible name? They don't call it binding energy in photoelectric effect.
They call it the,
Have you heard that term when you were doing photoelectric effect?
Work function.
Oh, wait, no, I didn't know that.
Yes.
Okay, it might be that it is such a terrible name that Carlos and/or Marcus just deleted it from 4C and never used it.
Yeah, that's terrible. I didn't know that.
Okay, yes, when you are reading about the photoelectric effect and you read about this idea of the work function of a metal, what that means is the binding energy of the electrons in that metal.
That's a really terrible name.
Yes, it's a terrible name. I mean, I guess work isn't all that terrible because work is synonymous with energy, and okay, so fine, it's energy.
But is it a function?
What's it a function of? Yeah, it's not a function of anything except, I guess, for what type of metal it is. Aluminum has a work function of such and such number of EVs. Iron has a work function of such and such a different number of EVs or whatever. But I tell you that name because you will come across this when you are reading Tipler or any other source that you tackle on this. It's an awful name. I don't know where they came up with it. It's as bad as electrical potential and then some. But in any case, I might say the symbol we use for work function is a capital phi. And I might say that phi for this particular type of metal, and again, the only thing it's a function of, the only thing it depends on, is what type of metal we're using here. And maybe it will be, let's just say 4 electron volts. So EVs are a familiar energy unit. You can convert them into joules if you want, and all that kind of stuff. As I'm shining this light on the metal, you would think, okay, so I've got to give one of these electrons a certain amount of energy to get it out of there. I've got to give it positive energy that equals that negative binding energy that it had. Presumably, if I made this light more intense, I'd be more likely to be able to get that electron out of there. I made it more concentrated. So they try, let me shine visible light on it. Maybe no electrons pop out. Let me make the visible light 100 times more intense, and still you're not freeing any electrons. You say, that's weird, because just the other day I was running this experiment, under slightly different conditions, and I was freeing electrons. Why can't I anymore? Well, you look back over your notes the other day, and the other day, actually, your light was nowhere near as intense as it is today. So it should have been harder for you to free electrons. The only difference is the other day you were using violet light, and today you're using red light. But the violet light wasn't even all that bright, yet it was able to knock electrons free. Yes, people realized as they were looking at this that for each given type of metal, there was kind of a frequency cutoff. Light below a given frequency would never manage to eject any electrons. Light above that frequency could eject electrons. Even if it was really dim light, it would eject only a thin trickle of electrons. It wouldn't eject very many of them. But still, even very dim violet light might be able to eject the electrons. Even very bright red or green light would not be able to.
It's like the different steps, right?
Well, what this came down to is Einstein's interpretation of this whole thing is that the light itself is coming in these discrete energy packets. People already were sniffing around the idea that when matter gives off light, it gives off the light in discrete chunks of energy. That if I've got an element which gives off light of frequency 4 times 10 to the 14th hertz or something like that, then it turns out that yes, the atoms that are giving off that light will only give it off in chunks of a certain size. Einstein ended up saying, no, it goes deeper than that. Quantization is not about how much light an element is capable of giving off at a time or anything like that. It's a feature of the light waves itself. A light wave of a given frequency only carries energy in chunks of a finite size, and you can never break those. You can never subdivide those chunks any farther. What's the size of those chunks? Well, first off, he said, I need a better name than chunks. I'll call them photons. But Einstein said, okay, the model that would explain the photoelectric effect is if the energy of a given photon.
Light chunks or photon.
Marcus called them lumps.
Okay, the energy of a given lump.
Which is, I feel like it makes more sense about what it actually is. Photon is so hard to visualize.
And also, photon sounds like I'm saying the word proton, and just so yes, no matter what we end up calling them in the long run, photons and protons will always remain very separate types of particles. And the energy of one of those lumps of light is going to be Planck's constant times its frequency. And why is it that low-frequency light cannot liberate electrons from this metal? It's because if...
You say Planck, too.
Planck?
Isn't it with an A?
It's definitely spelled with an A. I pronounce it Planck. Do you pronounce it?
You say Planck. I thought you said Planck.
Planck.
Oh, do you?
Josh says Planck. And I couldn't figure it out.
I say Planck.
I say Planck, but I'm not 100% sure I'm saying it right.
I don't know.
Is he French? Right.
Dutch.
Dutch.
Max Planck. Dutch or German, one or the other.
Planck.
Sorry.
Max Planck.
I don't know.
Yeah, not important. Just, commentary from the peanut gallery over here.
You can't eat peanuts.
Sure.
But if this is less than the work function, no electrons can ever be liberated. Was that?
Nothing.
It's less than the binding energy.
Yeah.
Yeah.
Now you could say, well, wait a minute.
Makes sense.
What if one electron catches 2 photons? Then, if each one is say 60% binding energy, if it catches 2 of them, couldn't that give it enough energy that it could break free? The answer actually is yes, but it's also just that when you illuminate a metal surface with light, the chance of a given electron catching 2 photons is so minuscule that I can ignore it. And you say, well, catching 2 photons, if I shine the light for a long enough time, couldn't an electron eventually have caught 2 photons? But you'd say, well, there's a relaxation time. After an electron absorbs a photon, it's going to be bouncing around, ricocheting off other particles in the metal, and it's going to re-randomize that energy. It's going to share it out with its neighbors. Essentially, it's going to turn that energy that it just absorbed into thermal energy by sharing it at random with all the other particles in there. So you'd say, well, there's a time limit on how long you've got to absorb that second photon. You've got to still have the energy that you got from the first one. So the chance of absorbing 2 photons within that brief window of time before you've thermalized the energy, as they say, you've randomized it back into thermal energy, is small enough that I can kind of assume that it never happens. So if the energy that I'm giving it is less than the work function, a more intense beam of light at that same frequency would have more photons in it. Because how do I measure intensity? What are the units on intensity for a light wave?
Area, energy, it's fluff. It's like energy into an area.
Yeah, energy per area per time, because it's saying how much energy do I deliver per second into a given area. Watts per square meter are the traditional unit of it. In fact, if you install like photovoltaic systems, you'll say, oh yeah, the intensity of sunlight at sea level is right around 1,000 watts per square meter. So oh yes, if I were to increase the intensity, well, it means I'm delivering more energy per second per square meter. If each photon has a finite amount of energy and I can't change that at a given frequency, then increasing the intensity must just mean I'm delivering more photons per second. And you could just run the conversion factor. You could say, okay, I'm delivering a certain number of photons per second per square meter, and each photon contains such and such an amount of energy. Great, energy per photon times photons per second per blah, blah, blah. Cancel the photon, now I've got energy per second per blah, blah, blah. So now I've got intensity. So yeah, intensity is kind of quantifiably and easily calculatable, related to the number of photons per second that you're sending down on there. So I need 2 conditions if I'm going to be liberating electrons. I need an individual photon to have enough energy to liberate an electron, and then if I then say how many electrons will I liberate per second, well, I can say, okay, now how many photons am I sending per second, and what's the probability of each one of them liberating an electron, and I can go from there. So, yes?
Just kind of back to the quantized part. You're saying that light has a specific amount of energy, and that's what you mean by
I am saying that a lump of that light has a specific amount of energy.
Oh, like a section of that light?
Wrapping your mind around what I mean by a lump of light was, of course, a huge challenge for the people at the time also. What do I mean by a photon? It means, well, if I'm thinking of the light as this classical wave of electric and magnetic fields, it doesn't have lumps. And again, by lump, I don't mean a cycle or a peak on the sine wave or something like that. No, I mean something that doesn't exist in waves, or at least I never thought it existed in waves. I mean that I can only have that wave in certain quantized amounts. Okay. And so here you'd say, how do I draw a photon? I might draw a little wave packet like that. I'm not saying each of those bumps is a photon, but I'm saying kind of this region that I've drawn where my E and B fields kind of grow up out of nowhere, and they're high in this region, they fade out again. That could be kind of a semi-classical picture I might have in my head of a photon. But then you say, well, couldn't I just kind of, draw another one, but the E and B fields have half that amplitude? No, I can't. This is a fundamental unit of energy. That maybe the way I've drawn it is not right, but I'd say, okay, there is no actual way I can draw you a photon. It's not a classical concept, but you cannot subdivide that light wave any further. If I'm shining a green laser at the wall, and you say, that's a little bit too bright, can you turn it down by 10%? Yeah, sure I can. Can you turn it down by another 2%? Yeah. Okay, that's a little too far, can you raise it by 1/100th of a percent? Yeah, I can do that. I can kind of alter the intensity of that light any way I want, because at a macroscopic level like I've been doing here, I'm sending so many photons per second that if you tell me, can you change it by such and such a small fraction, I always can. But then I start turning it down, and you say, make that light dimmer and dimmer and dimmer, and you get to the point, and you say, hey, you're almost there. Can you just, over the last 1 second, you sent me a certain amount of energy. Over the next 1 second, can you send me 90% that much? And all of a sudden I say no. You say, what, is the dial not going any further? No, it turns out over the last 1 second I sent you a single photon. If you want me to send you some energy over the next 1 second, I can send you no photons, or 1 photon, or 2 photons. I can't send you 90% of a photon. There is no such thing. Light comes in these discrete lumps. And this doesn't have to do with the device only able to produce light at those levels. I mean, again, people have been kind of sniffing around the concept that light was quantized. This is why they call h-bar Planck's constant, not Einstein's constant, Max Planck had, as he was working with blackbody radiation and the emission spectra of elements and all this kind of thing, had been wrestling with the idea that apparently when an atom emits light, it emits it in these quantized chunks. The thing that, the way Einstein changed this model that was kind of a big conceptual breakthrough, was he saying, no, this is not about the ability to emit light. It's about the light waves themselves. They can only exist in these quantized clumps. So we call them photons. Marcus calls them lumps. What they are, what you should be picturing in your mind, really has no classical equivalent. Waves don't come in lumps classically. And in fact, a quick way of kind of ridding yourself of certain misconceptions is when I say waves don't classically come in lumps, if you find yourself saying, well, yes, they do, and maybe what you meant was like 1 cycle of a wave is 1 lump, and I can have 1 cycle of a wave, or 2 cycles, or 3 cycles. No, that's not what we meant. Essentially, anything which is a feature of classical waves is not what we mean by quantized waves in quantum mechanics. The wave quantization is something that just had no classical equivalent. But somehow, yes, this light is still a wave made of electric and magnetic fields. I can use Maxwell's equations to kind of analyze the behavior of those fields within the light wave. But somehow, this little packet of energy comes in finite packages. And once you get down toward, and you're starting to notice individual photons of light, you can't subdivide them any further. Now, if you're saying, man, but I wanted a photon of light that had less energy, I could give you one, but it would also have to have a different frequency. So each frequency of light kind of has a currency denomination. In many ways, you could say, quantization of light in quantum mechanics is like quantization of currency. If we're negotiating a price on a car, and you say, well, can you bring that down 10%? And you say, can you bring that down another 0.5% and all that? The person you're negotiating the car price with can probably do all those things until you start asking for changes that are less than a penny. And then they're going to say, well, no, I can't. It's the old price, or it's 1 penny lower, but I can't do anything in between.
Okay, so like a photon can only have certain energies.
A light wave can only have certain energies. I mean, a photon, a light wave has certain energies which are multiples of the energy of 1 photon.
The photon limits the way light can be broken down.
A photon is like a penny's worth of light.
Okay.
You can't break it down any further, except that in the same way that, I could say, well, here's a nickel. Can you break that down any further? Not while remaining nickels. I could say, here's a bag of nickels. They say, can you give me 10% more? Yeah. Can you give me 5% less? Yeah. Here's and we keep negotiating until I'm giving you a single nickel, and you say, can you give me 10% less? Well, no, I can't, but we could change denominations. Maybe I'm going to pay you in pennies, or I'm going to pay you in, my teacher in grade school used to tell me there used to be little plastic coins called mills. I think she was either trolling or confused. But she was basing it on the fact that towns will enact a mill levy, where that would be like a 1/10 of a cent tax on each dollar of a transaction. And she was telling us that, that's because there used to be coins called mills, and they were made of plastic, and they were worth 1/10 of a penny. yeah, I don't know if it was intentional or if somehow she was misinformed. But you could say, all right, in actual currency, there's only certain denominations. In photons, you've got an infinite number of denominations. Depending on the frequency of the light you're talking about, each frequency of light is like a new type of coin with a new denomination.
Okay.
But if I'm going to stick with a given frequency, this is saying, okay, now we're going to exchange quarters. We're not going to exchange any other type of coin here. Then we're stuck exchanging multiples of 25 cents.
Okay.
Which is fine for coins. Coins do behave that way. Classical waves do not behave this way. So this was definitely a split between classical wave behavior and the way things like light waves apparently behave in quantum mechanics.
What do we do with this information?
The most important thing you do with it is you introduce the idea of photons into your conceptual vocabulary. You say light does come in photons. Now, if we give you problems that are about the photoelectric effect specifically, then you'd say, well, what was the data that convinced people that light's quantized like this? You could ask questions such as, well, if I'm sending that light down on the surface of the metal, if I were to graph how many electrons escape per second as a function of the intensity of the light, it would always be linear. If I make the light twice as intense, I always get twice as many electrons escaping per second. Mm-hmm. Now, if you say, well, what if you make the light a different frequency? It'll still give you a linear function, but with a different slope. And interestingly, for higher frequency light, you might expect me to say more electrons escape each second because I give you higher energy photons, but actually fewer electrons would escape each second. Because if we say, okay, this axis is intensity, so we draw a vertical line there, this would be saying compare different frequencies all at the same intensity, how many electrons escape. The high frequency light, well, I'm putting all my energy into this relatively small number of photons. As I go to a lower frequency light, that same amount of energy is actually giving me a bigger number of photons. Yet lower frequency, bigger number of photons. So I'm having more electrons escape until I lower my frequency and I drop below that threshold frequency, and then all of a sudden 0 photons escape. So again, this makes sense once you know that, 0 electrons escape. This makes sense once you know that photons exist. When they did not yet know that photons exist, and they were trying to think of light as a classical wave, this was making no sense at all. This was absolutely bewildering data. Now, you could ask another thing. You could say, okay, if I do allow electrons to escape, how much energy have they got as they leave that metal? Now, the answer there would depend on what? If I say, okay, I'm going to shine a light wave on a metal, sometimes no electrons escape, and then you just can't answer this next question. Mm-hmm. Sometimes lots of electrons escape, sometimes only a few of them escape. But I'm not interested right now in how many of them there are. I'm interested in how fast those electrons are going, how much energy do they have as they break free from that metal. What would that depend on? How would you calculate that?
Depend on the binding energy and the energy of the photon?
Yeah. You'd say the energy of an escaping electron actually what you'd usually find is there could be a whole range of different energies that escaping electron could have. But if I want to know what is the maximum energy it might have, well, the most energy it can absorb from a photon is going to be 100% of the energy the photon carried, which is the HF. But then it's going to have to give up some of that energy to escape from the metal. So I'm going to subtract off that binding energy. If it takes 4 EVs to escape, and I gave it 7 EVs, then it'll have 3 EVs left after breaking that bond. If you wanted, you could say, yeah, once again, should say binding energy, I think of as a form of negative potential energy. It started with a potential energy of negative 4 EVs. I gave it 7 EVs from the photon. Great, it now has 3 EVs. Or maybe it has less than that for a couple of reasons. Maybe it didn't absorb 100% of the energy that photon had. Maybe it scattered the photon. Or, more commonly, yeah, it absorbed 100% of the energy, but it bounced around for a while, ricocheting off other electrons before it actually broke free of the metal, and it lost some of that energy along the way. So this wouldn't be the predicted definite energy of that escaping electron, but this would be the maximum energy that escaping electron could have. Now, how are you going to measure the maximum energy that the electron could have? So here it's as a function of the frequency of the light. If I plot that maximum energy, it should look something like that. As I raise the frequency, the energy of the photon would have followed that dotted line, but then I've got to subtract off the binding energy so that the energy of the escaping electron follows this lower line. And of course, the electron can't have negative energy, so if I drop below that threshold frequency, I just don't get any escaping electrons in the first place. So this would be the threshold, and its value would be binding energy over Planck's constant. Just setting that those two sides equal. How would I actually carry out this experiment? How would I know how fast those electrons were going? So that could I get data? If this is the prediction that I would make for my photon model, can I get data to see if that prediction actually comes true? Well, it's kind of hard because electrons are teeny. So trying to measure how fast they're going with a stopwatch or something like that wasn't really something you could do. So how did they actually, how would you actually try to measure the energy of that escaping electron? This is where that whole stopping potential came in. So if you say, oh yeah, often I will talk to people, especially if they study photoelectric effect in chemistry class, and I'll say, what was the most important thing about the photoelectric effect? What did they learn from it? And they said, well, it was how you would learn about the stopping potential. No. The stopping potential is kind of how you would learn about the properties of photons, but no, the stopping potential was just a trick that the experimenters came up with to measure the energy of those escaping electrons. How would I measure the energy of, if I've got somebody who's rolling bowling balls through this room, and I want to know how much kinetic energy they have, well, if I can, bowling balls are slow moving and I can see them and I can probably just time them with a stopwatch, but if I can't, one trick I could do would be to put a hill, a speed bump partway across the room. And if the bowling ball can go over the speed bump, then it must have had at least a certain minimum amount of potential energy. If no bowling balls can go over the speed bump, then I know that none of them had that much kinetic energy. So this is what we would be doing here. We would put a speed bump. We'd say, okay, how am I going to measure those electrons in the first place? Often you would measure them by letting those escaping electrons, which are too small to see, hit an electrode over here, and then you'd have a wire going back to your original chunk of metal, and in that wire you would put whatever was the highest precision ammeter you were capable of building at the time. So this is how you could see that electrons were escaping in the first place, is if they are escaping, they should hit that electrode, follow the wire back to the original metal, since the original metal is now slightly positive, so they'll want to get back there, and you'll be able to see on your ammeter that current of flowing electrons. How would I put a speed bump here to keep those electrons from completing the circuit? I could make that electrode negatively charged, so it'll repel electrons. And the more negative charge I put on it, the more strongly it will repel them, so the faster they would have had to be going to get there in the first place. So, if I put this thing at potential, I might call the, let's see, oh yeah, we use the word lump for photons, we haven't used the word bump yet. So I can say this is potential V speed bump. That's not a velocity, that's a voltage. How fast are the electrons going once they reach that, that electrode? Well, I just do energy conservation. I'd say, well, whatever their original kinetic energy was, how has their potential energy changed by Q times V speed bump? If V speed bump is positive and Q is negative, you'd say actually that means their potential energy dropped, so they gained kinetic energy as they were approaching that. So V speed bump would presumably usually be a negative voltage because that means that it would start repelling electrons. And in order to figure out the maximum amount of kinetic energy they could have started with, I would just look at the height of that potential barrier. So they start with, an electron leaving the metal has energy that could be anywhere up to Ke max, plus potential energy, which would be 0. The electron arriving at my target has now kinetic energy 0 if it barely made it to the top of that speed bump. But what's its potential energy? Q electron times V speed bump. And what they found was that if you do a graph of that maximum kinetic energy as a function of the frequency of the light that you were shining there, you do get this behavior. You find that below a certain frequency, you got no electrons whatsoever. Above that frequency, you get electrons, and as you ramp the frequency up further, you don't get more electrons. Actually, you get fewer, interestingly, because you're putting all your energy into a smaller lump of high-energy photons. So you don't get more electrons, but you get electrons which are moving faster. Their maximum kinetic energy goes up as you ramp the frequency up. Now, very often they will say, so how do I measure that Ke max? Well, I do it by adjusting the speed bump until the electrons stop, and at that exact voltage where I don't get any electrons anymore, making the speed bump just high enough to stop the last of the bowling balls. That would be how you'd measure your Ke max. So if you're looking at historical data from these photoelectric effect experiments, they might not put Ke max here. They might put V stopping. In other words, how high do I need to make that speed bump in order to stop those electrons? Two ways of saying the same thing. The whole point of that stopping voltage was it tells you how much kinetic energy they started with. And, well, that would just mean, so, V stopping would be the same thing as Ke max over the charge of an electron. So then you say my threshold frequency would still be the same as before. F threshold. What would be the slope of this line? Well, the slope of your line for Ke max so this would be HF minus your work function. So the slope of the line, if you graph Ke max, would always just be H. It would tell you Planck's constant. The slope of the line, if you're graphing stopping voltage, would be Planck's constant over Q. Now, very often, kind of in the name of tying things to concrete historical experimental results, they'll make an admirable effort to tie things into concrete history. And they'll say, what we're going to show you is a lot of problems where you get a graph of stopping voltage versus frequency. The problem with that, I mean, the nice thing about that is, yeah, this is historically how this stuff was discovered. The bad thing about that is that's exactly how the chemistry students all walk away thinking that apparently the photoelectric effect was all about how to study the stopping voltage. No, the stopping voltage was how you measured that maximum kinetic energy. And the reason you cared about the maximum kinetic energy wasn't that you've got a fixation on making these electrons go as fast as possible as they escape the metal. It's because this was the evidence that made people realize that light is quantized in the first place. This whole network of results that we've been showing here make perfect sense if we say that light comes in lumps of energy HF, and makes no sense if you think of light as a continuous wave that can be tuned to whatever amount of energy that you want. So the big historical punchline to these experiments was nothing to do with stopping voltage, nothing to do with the actual kinetic energy the electrons were going out with. That was all just clues to the kind of big change that people needed to make in their concept of reality, which was that, yeah, apparently light waves are quantized. A light wave cannot carry whatever amount of energy you want it to. A light wave carries these discrete lumps of energy of size, Planck's constant times the frequency, and you can't subdivide it any further than that. You're giving me a look of...
I get the like quarters analogy, like we'd only be dealing with currency in quarters or pennies or nickels or whatever, and then we couldn't subdivide that. But are we supposed to? And I guess I'm just trying to think of it classically and stop working.
Yes, and it's, in fact, if you try to think of it classically and you say, oh yeah, it does work, I see just why light would behave this way, if you think you can see why it would behave this way from a classical point of view, it means you are misunderstanding what we're saying about the photon model. So
Yeah.
the fact that you try to think of it classically and fail means you're on the right track. You try to think of it classically and succeed, either you have this wonderful insight that I hope you'll share with the rest of us on how to bridge the classical picture with quantum mechanics and make it all make sense, or it means that you've misunderstood the quantum mechanics.
Well, the wave doesn't make sense because it's colliding with an electron, and then
Yes, now you'd say, okay, so for a classical wave of electric and magnetic fields,
yeah,
the electric fields are pushing on the electron as they go by. So your light wave's coming through. Your light wave is this oscillating pattern of E fields and B fields that keep switching direction. As they interact with that charged particle, they're pushing it. And you can get some kind of resonance effect where it's picking up energy from the wave. And if you shine that wave for long enough, the particle picks up enough energy that it escapes. That makes perfect sense with a classical wave. The thing that doesn't make sense is that the wave only has, a certain amount of energy it can give to that electron.
yeah.
Classical waves aren't quantized. You can kind of say, depending on how long it interacts with the electron and what the amplitude of that wave is, it could give it whatever, as much or as little energy as the circumstances say it'll give it. Instead, in quantum mechanics, we're saying, no, you've got this electron. It's got all those properties of a classical wave. It's got a wavelength. It's got a frequency. You can set up interference patterns between light waves and all that. So it's not that we're saying, no, we were just wrong to think it was ever a wave. But even though it is a wave, at the same time, the energy it can deliver you is not continuous. It comes in these discrete clumps. It can give you 0 photons worth of energy, 1 photon, 2 photons, 3 photons. There is no such thing as 2.5 photons in that frequency. And that is something that is pretty much impossible to reconcile with the classical point of view while keeping the classical point of view. You can't say, oh yeah, I should have known all along that light waves would behave that way because of such and such. If that such and such is part of their classical behavior, you shouldn't have known they would behave that way. Classically, they're not supposed to.
You're kind of making it sound like it's particles, but it's
Yes, photons are particles of light. Only, and then you say, well, okay, so I get why particles could behave like waves. The particle could just be going in a slalom pattern or something. No, again, that would be anything that you can imagine. If you say, oh yeah, I'm just picturing a classical particle, and I see just how it would behave like a wave. No, you're not. The classical particle going in a slalom pattern, it's just a classical particle following a slalom trajectory. That's not the same thing as waves. You couldn't set up an interference pattern. If I had two classical particles that were both doing slalom trajectories, I can't set up an interference where their trajectories cancel each other out or something like that. That's not what trajectories do, even if they're out of phase with each other. Now I've just got two particles. They're kind of, tracing trajectories like that. Photons have a bunch of properties that we would associate with classical particles. They manifest in one particular point. If I send a photon and I measure it with a piece of photographic film, it's not going to be spread all over that entire photographic film. That photon will leave a dot at one point on the film. In that sense, it's behaving like a classical particle. Mm-hmm. On the other hand, a photon can create interference patterns. I won't even just say two photons can interfere with each other. A single photon, if I send it through something that diffracts it out and lets it follow more than one path, a single photon creates interference patterns because the single photon is still a wave phenomenon.
It's kind of like its components that are creating the pattern.
Yeah, but for the most part, we'd say, man, any way that humans have come up with of saying, I can visualize in my mind an entity that has all the properties of a classical particle that photons show, and also has all the particles of classical wave that photons show. I'm not saying quit trying to do that. And if you've got a way of explaining it, man, explain it, please. I would love to hear that. But it is worth knowing that since a lot of generations of scientists who have worked on this is something that is kind of fundamentally tough, verging on impossible to wrap a mind which was trained on classical experience around. That we're seeing something here that you would just not expect based on classical observations of the world. Now, this doesn't mean it's weird, because no, it's exactly what happens when you're looking at fundamental particles. But since our own intuition and experience was not trained on fundamental particles, it was trained on macroscopic objects, it's very hard for us to come to grips with this. There will be people who will tell you that I'm making that case too strongly, that I'm mystifying quantum mechanics, and I'm making it sound like it's something just logic breaking and weird, which it's not. So I'll say, okay, no, I don't want to fall into the trap of quantum mysticism, of making it sound like I've talked about magic here or something like that. It's not magic. It's the way nature works. Well, I think it's not magic, but I will say, if you come up with an easy way to wrap your mind around this, probably it means that you have misunderstood some aspect of this. By the way, so let's see, probably have to take off soon, but
I'm just standing.
The whole way of interpreting all of these pieces of evidence and saying, oh yeah, this all makes perfect sense if photons are quantized, you can test that by taking something else which is quantized. So you could say, all right, instead of dropping photons onto the surface of a metal, I can imagine doing a thought experiment where I am dropping envelopes of money onto a big crowded train station. And the electrons in this metal, by the way, they've got a little bit of kinetic energy of their own, but it turns out that at room temperature, the kinetic energy of a typical electron in metal is about 1/40th of an eV, whereas the work function of most metals is kind of several EVs. So the electrons have got not even very much of a fraction of the energy they would need to escape. So essentially, the chance of an electron just randomly through kinetic energy it picked up from collisions escaping the metal is pretty close to zero. So I could have this train station, which is full of people, and the people might each have, a little bit of money in their pockets, and they might be working and setting up businesses in the train station and making a little bit of extra money. But the cost of the train tickets is just out of line. The amount of money that the people are carrying on an everyday basis is a tiny fraction of the price of a train ticket. So nobody is ever going to be able to escape from this giant train station. So in order to help, I decided to fly overhead with a helicopter and start dropping packets of money. Now, I can make the conditions of my helicopter experiment match as well as possible with the conditions of this photoelectric effect experiment. We said no electron ever receives more than one photon, because in the time it would take to receive the next one, it's probably shared its energy out. So I say, okay, drop these envelopes, but the envelopes are sparse, and there's a lot of people in the train station, so no one person ever catches more than one envelope, or at least if they do at some time much later in their life, they catch the first envelope, and by the time there's any chance they'll catch another one, they've already spent the money and randomized it out among the other people in the train station. So so each person has kind of only one chance to get on the train. If I'm dropping envelopes that contain $20 in cash, and the train tickets cost $30, nobody ever gets on the train. I can be adding some cash to their economy in the same way that light, which is below that threshold frequency, can be adding some thermal energy. It can be warming up the surface of that metal, but it won't actually eject any electrons. Mm-hmm. Now, on the other hand, if the train tickets cost $30 and I'm dropping envelopes that have $38, well then all of a sudden people can start getting on the train. Even if I'm dropping less money than I was yesterday. Yesterday I was spending, tens of thousands of dollars dropping these $20 envelopes and nobody got on the train. Today I showed up with less of a budget. I'm only dropping, a smaller number of envelopes, but they've each got $38. Even though it's less total money than before, now I start noticing people are escaping from the train station. How much money would these people have in their pockets as they leave? $8 maximum, exactly. They might have spent part of it, before getting on the train, but the maximum amount of money they could have is going to be the money in the envelope, and the HF is, if every envelope contains $38, that's like saying every photon at this frequency all have the same amount of energy. So HF, the money in the envelope, is like my photon energy. The work function is like the price of that train ticket. And I could say, okay, this would make sense. The amount of remaining money they have, the maximum amount of cash they have, would be following a curve like this. As I put more money into the envelopes on different days when I run different versions of this experiment, the total amount of cash they're left with would rise, and it would just be, again, always less than the amount I dropped by the price of that train ticket. So everything, the implications, the idea that light, which we always thought of as a classical wave, is now also a particle, the implications of this should be kind of mind-blowing. The interpretation of the experiment is not. Interpreting this experiment as evidence that light is quantized is as straightforward as interpreting my experience at the train station as evidence that each of these envelopes of money must have contained the amount of money that I think it did.
I feel like the analogy makes sense, but the actual photon things.
The actual photon thing is fucking weird. I mean, today we're used to thinking of photons. Photons are on our list of particles and all that kind of thing. But if you said, well, yeah, but can you tell me what it is that you picture in your head that allows, tell me the picture you have of light that is consistent with everything we know about the wave properties of light and is also consistent with everything we know about the particle properties of light. To this day, 100 years into the progress in quantum mechanics, a lot of better minds than mine have wrestled with this and tried to explain it out. I still don't have a consistent picture. In fact, what I would say is, it's when you're doing quantum mechanics, it's not that you want to give up the idea that you form these kind of visual mental models as you go along, and that you use the mental models to guide your understanding of the equations behind them. But there is no single mental model that works. in Newtonian mechanics, if I'm trying to understand the way, a planetary orbit works, all I need to do is get really good at thinking about the force of gravity pulling on it. How is that force going to alter the velocity? The acceleration is going to be that force over m. As my planet arcs in closer to the sun on this part of its orbit, it's feeling a stronger force. As it's approaching the sun, the force pulling on it is in this direction that's kind of partly forwards and partly sideways. So it is the planet is changing direction, but it's also speeding up. This whole, I can come up with a picture of how Newtonian mechanics works, and the better I am at kind of forming and analyzing these pictures, the closer I'm going to get to the right answer. In quantum mechanics, I can come up with a picture of how light waves work. I'm thinking of a wave of electromagnetic fields, and I'm kind of thinking as the E field changes, that changing E field is then inducing a magnetic field, but as the magnetic field changes, that's inducing a new E field, and it works great until I run into a situation where quantization is important, and then that picture just doesn't work anymore. And for quantization, I think of photons as these little lumps of energy, and that works great until I have a situation where interference is important, and then that picture doesn't help me understand interference. The best answer I can come up with quantization is in quantum mechanics for the question of, is it still worth forming these mental models? Yeah, but there is no one mental model that answers every question. So you need a sort of agility also, where you are jumping back and forth between several different visualizable models, and each one kind of is really good at explaining some aspects of the behavior, and is really bad at explaining other aspects of the behavior. And in some problems, you say, okay, no, that's okay. All I need is that electromagnetic wave model. Or all I need is the little lumps of energy model. For other problems, you need both of them, and you're kind of saying, well, let me get a little crucial piece of insight from this model, and then let me jump my mind over to this other model and get a little piece of insight there, and then jump back. It is a more energetic piece of mental exercise sometimes to try to model a quantum mechanics problem in your head than it ever was trying to model a classical mechanics problem in your head. Doesn't mean that we should stop doing it, and it doesn't mean that quantum mechanics is magic, but it just means, hey, our experience has not left us with a single mental model that encompasses all this, but sometimes by patching together several models and kind of knowing from experience when to jump off on one log and hope that you land on the other log, you can build up a very powerful intuition on how quantum mechanics works, just like you can build up a very powerful intuition on classical things. But it can be a dicier game to play. So this was the first big kind of new ingredient to reality that people had to wrap our minds around once quantum mechanics was discovered, was the idea that photons, which we had always thought of as just pure classical waves, somehow also have the properties of particles. Now, the de Broglie model that you talked about next was the discovery that things like electrons, which we had always thought of as pure classical particles, also have the properties of waves. And again, that is kind of just as hard to wrap your mind around. One piece of good news there is the properties of electrons and the property of photons. I mean, there's differences between them, but in terms of the quantum weirdness that they bring with them, they're both the same thing. A photon is this wavicle, whatever you want to call it. It's this thing which is both a wave and a particle. An electron is also this thing which is both a wave and a particle, and the ways in which, you find your mind butting up against the wave properties where you're trying to think of it as a particle and vice versa are the same for photons and electrons. The mystery of quantum mechanics is pretty much the same for both those particles. So we will talk next time about what was the evidence that started us thinking along the lines that electrons must be waves, just like photons must be particles, Schrodinger's equation will turn out to be the equation you'll use to treat the electrons as a wave. The solution to Schrodinger's equation is kind of saying, here's this sinusoidally oscillating quantity that kind of represents the wave property of that electron, and here's the set of equations you use for saying, given a potential energy function, given the actual circumstances of a given problem, what is this electron wave going to look like? Where, is it? What regions will it be the most intense in? How will the intensity change over space and all that? So Schrodinger's photoelectric effect will be kind of the initial evidence that light waves are also particles. The whole de Broglie phenomenon will be the initial evidence that electrons are also waves. And the Schrodinger equation will be the way you say, hey, quantitatively, how do I actually calculate the wave properties of this electron? Now, I can distribute for you the first problem set. I will go ahead and email you both the first problem set on the quantum mechanics side of this. At first, don't feel like I'd say writing up the problems is not an immediate priority. You can say let's focus on wrapping up the relativity stuff for most of our written work here. But reading over them and saying, can I understand how I would answer this question based on what we've been talking about in lecture is probably a good thing.
Okay.
Okay.
Sorry, I feel like I'm kind of like a dead fish audience. I'm tired.
Oh yeah, no worries. Well, it's